All right, welcome to a new week. This is a week with just one lecture in it because I'm trying to keep us in sync with my other class, and we're pretending, right, that this is a Monday-Wednesday class, and Monday is a holiday. So we just have one lecture this week, and that is where we shall finish this set of slides. Are we ready? Let's do it. So down here is where we left off, and I want to talk about bits and bytes and things today. Talking about how much stuff we can put inside of a type. Okay, so like, what does it mean to be an int deep down in binary? Okay, so here's a table that I will show you now, and then again later, after I teach you about all these fancy words, if you haven't heard of them before. So this table will make more sense by the time I'm done explaining things. But here's where I'm trying to go with all of this. An int, for example, is made up of 4 bytes, and that is 32 bits. We'll learn about all that conversion and stuff. And every integer is within a certain range. You cannot store infinitely many numbers inside of an integer, just some pretty small numbers to some pretty big numbers. You can't go any larger than those, though. Okay? That's the range of numbers that an int can hold. Char, for example, it has fewer bytes inside of it, and so a char can only hold 256 different numbers. Interesting, huh? A double has twice the amount of space as an int, but it's storing its numbers in a different way, and so it can store some pretty large numbers, and we've got a lot of decimal places too, about 16 digits of precision, we say. Okay? And then these are some other types that you might see in your book or on the internet. Those exist. Those hold whole numbers just like ints, but we don't really use them in this class. And so now you might be wondering, what in the world is a byte? So let's get into this. Let's talk about all that. Okay. So, and before I move on, there's also a float type that is 4 bytes long, and it holds floating point numbers just like doubles. So yeah, the first thing I want to talk about before we get into what a byte is I want to teach you this thing called base conversion, okay? Because binary is called base 2, and there are multiple bases. You can have infinitely many, right? One for every number. So let me show you how to convert between bases, right? So a base is just when you make a new place in your number system. So our numbers that we like to count with, that we know and love, are in base 10 right now, and that is because we have 10 digits. Okay, we have 0 through 9, and that makes 10. So the second you want to add 1, 9 plus 1, you have to make a new place, okay? And so we only had 10 digits to work with. The second we want to go one bigger than that last digit, we have to add a new place, and so that makes 10 for us, right? Binary is called base 2, and so the only digits that you get to work with in binary are zeros and ones, okay? So you can count 0, 1, and then the second you get past 1, you don't have any more digits to work with in binary, so you have to make immediately a new place, and so it looks like 10, but it's just 1, 0, okay? And so to differentiate between the numbers that we know are decimal numbers and numbers in another base, I'm going to use subscripts. So this is 1, 0 subscript 2, which is 1, 0 in binary. 1, 0 base 2, we say. And this number, 1, 0, 10 for us, right? I'll use the subscript 10 to mean we're talking about base 10, decimal. So that's the decimal 10. This is the binary 1, 0, which is 2, right? So we'll get into conversion in a second, don't worry. But there's plenty of other bases too, right? We have like base 5. That exists. You can write all your numbers in base 5, and that lets you use 0, 1, 2, 3, and 4 as your digits. That's all you get, okay? And so remember that numbers written in different bases, even though they might look the same, like 100 in decimal, that's not the same as 100 base 5. That's a completely different number. Same with 100 base 2, okay? So I'll show you what all this means, but that is the notation, all right? When we're talking about binary, we've made up some extra special words just for binary. Whenever we have a digit, and we're talking about a single digit of a binary number, instead of saying binary digit, we say, we just kind of get rid of some intermediate characters and we call it a bit, okay? And so a single binary digit is a bit, and a byte is 8 bits, okay? So here are Here is a 4-bit number. A 4-bit binary number, base 2, right? So a byte is just made up of 8 bits. So let me make a random byte in binary. Is that 8 yet? 7. So this is 1 byte. I don't know what number it is. We'd have to calculate it, but it's 8 bits long. Okay? That's the idea. And so in a byte, you can hold the following. You can go from 0, 0, 0, 0, 0, 0, 0, 0, and you keep adding until you get to 1, 1, 1, 1, 1, 1, 1, 1, right? You only have 8 digits, 8 bits to work with. That's the smallest byte. That's the biggest byte. Okay? And so now let's talk about conversion. So if we have a binary number, how do we convert that to decimal? And the trick, I'll show you, is it goes back to elementary school when we learned how to break down numbers, like 1,234 in decimal. Do you remember how to break down that into its places? The 1, the 2, the 3, and the 4, and like the thousands place, the hundreds place, and all that stuff. Because that's really, what, 1,000 plus 200, you remember this? Plus 30 plus 4. That is what we want to do for binary, and that will let us convert. So we can go further than this, right? Once we learned about exponents, this is really 4 times 10 to the 0, right? Plus 3 times 10 to the 1, plus 2 times 10 squared, plus 1 times 10 to the 3rd. You see how that's working? So that's the thousands, the hundreds, the tens, the ones place. And wouldn't you notice that, look at what we're using here. We're taking the base to a certain power, because this is base 10, this is decimal. That's why you see a 10 everywhere with these exponents. If you follow the same process, you can convert a binary number to decimal so that we know really what it means. Okay? So let's do the same. So instead of 10 everywhere, we're going to say 2 everywhere. Okay? So it's usually the best to start from the right, like I was doing. So this last digit is the ones place in binary. Still, it's 0 times 2 to the 0, right? And then this is the 2 to the ones place, or the 2's place, I guess. So this is plus 1 times 2 to the 1. This place is 0 times 2 to the 2. This place is 0 times 2 to the 3. This place is 1 times 2 to the 4. And that is the number. That's, if we just do this math, it'll tell us in decimal what this number was, right? So it is 1 times 2 to the 4, which is 2, 4, 8, 16, plus a bunch of zeros, plus 1 times 2 to the 1, 1 times 2, so plus 2, which equals 18 base 10. So this number right here in binary is the equivalent of 18 base 10. Take some more digits because you don't have a lot to work with in binary. Does that make sense? That's how you convert. That's how you go from binary to decimal. Okay? And so I want you to try now. So give this one a try and pause the video, and I'll come back and show you the answer. So this is a 4-bit number, 1111, in binary, base 2. Convert that back to decimal, please. Excuse me. So working our way from right to left, as we do, this is 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 squared plus 1 times 2 to the 3. Yeah? Which is 8 plus 4 plus 2 plus 1, which is 15, base 10. Did you get that? So this is the biggest possible 4-bit number. Remember all these terms now? Not too bad, right? So this is where I tell you that this is the easy way. Going from binary to decimal is the easy way. If you want to go the other way, to take a decimal number and convert it to whatever its binary equivalent would be, then we got to do some fancy stuff, unfortunately. Okay, so let's talk about what we have to do. There's an algorithm involved. It's once you understand the algorithm, it's very easy to convert, but there's some new stuff we have to learn about first. Okay, so you've seen the slash. I've taught you about the slash for integer division. Like if I do 10 slash 2, that's 5, right? But there's an extra operator in C++, that's the percent sign. It has a slash inside of it, right? This means remainder or modulus, we say, okay? And what it does is, if you say this in C++, it calculates the remainder after dividing by a number. So it pretends to do 10 divided by 2, and instead of giving you back the answer, it gives you back the remainder, okay? So this is the modulus operator. So let me show you that in C++. Make a new lecture folder for today. Boop, boop. And, I don't know, modulus.cpp. So here is the normal integer division, right? If I do like 13 divided by 2, that'll give me whatever the answer is, right? Chopping off the decimal places. That's 6, but if I want the remainder after dividing by 2, whatever's left over, it's 6 remainder what? That's where this percent sign comes into play. So x mod y, we say. I say mod, short for modulus. X mod y is the remainder after dividing x by y. Okay? That's what's going on there. And so this is an odd number, so if you divide by 2, you have 1 left over. Does that make sense? So that is the modulus operator. And there's you can do this with anything. Like you can do 13 mod 5. And that's 3, right? Because 5 goes into 13 twice to make 10, and then there's 3 left over. So that's getting the remainder out after dividing. Okay? So that is going to be our key to extract or to convert a decimal number to a binary number. And the trick is to notice how we might extract the digits of this number by itself. Okay? So let me show you that algorithm, and then we'll convert that into a base conversion algorithm. So what I'd like to do right now is take this number and somehow extract the 4 just by itself, extract the 3 just by itself, extract the 2 just by itself, and the 1. Okay? We're extracting the decimal digits of this decimal number. And we can do that with integer division and modulus. Let me show you this. You have to do it backwards though. If I wanted to pick out the 4 of this number, I can use modulus 10. 1, 2, 3, 4. If I do mod 10, because this goes in 123 times, right? Because 1, 2, 3, 4, integer division by 10 is 123. There is 4 left over, right? And that'll get me the 4 that's in this number. That's quite nice. Then I need to somehow, because we just noticed that if we do this, we can always get the rightmost digit of a number. Now we need to somehow convert this number to 123. I just showed you that too, didn't I? So if you take this number now, 1, 2, 3, 4, integer divide by 10, you get 1, 2, 3. And then you can repeat the process of getting the rightmost digit. Okay? That's how I'm going to extract every digit of this decimal number. Okay? And this will help us eventually to base convert. So now I have 123 to work with. Then I can do 123 modulus 10 to get the rightmost digit, because it goes in 12 times, 120 with 3 left over. So I've got the 3, 1, 2, 3, integer divide by 10. That'll get rid of this 3, shift it away, make 12, because it's 12.3, right? It drops the 0.3. And then I can do this process all over again, 12 mod 10 to get the rightmost digit of 12 now, which is 2. 12 integer divide by 10 to get 1 mod 10. It doesn't go in any times at all. 0 remainder 1, right? So there's 1 left over. And then 1 integer divide by 10, shift away the 1 at the very end. That makes 0. And that's when you know you're done. Okay? So looking at this process, it's getting us the digits of of this number from right to left. Every time you do a modulus, you get the next digit. Boop, and you read it backwards. So this number was 1, 2, 3, 4. You see that? And then I stop my process. when I reach 0 after dividing. And what do you know? I see the base popping up again. Boop, boop. It's everywhere. This is how I extract the decimal digits from this number. I wonder, if I were to change this from 10 to 2, if I were to extract the binary digits, right? Maybe that's what you're thinking, and the answer is yes. That's the trick. This process works for every base. If you repeatedly divide and take the modulus by the base you want to convert to, you will successfully convert it. So if I want to convert this number to base 2, 15 to base 2, all I have to do is take the modulus and integer divide by 2 instead of 10. So I'm extracting the binary digits, the bits, instead of the decimal digits like I was. Okay? This is the hardest part of the algorithm, to just remember this stuff. But once you understand this, it makes sense. Okay? So start with 15, and then we're going to extract the rightmost bit of 15. We remember what it's supposed to be, right? It's 1, 1, 1, 1. So that's how we can check our answer. So 15 mod 2, modulus 2. What am I going to get? That's the rightmost bit of this number. Well, it's an odd number, so I'm going to get 1. You see that? And then I want to shift away that 1 bit. I want to get a smaller number that I can then convert to binary that builds, once I'm done, it builds up the full number, right? So I do 15 integer divide by 2, which is 7, right? 7.5, drop the 0.5. And then now I have 7 to work with. I just need to convert 7 to binary. And so I want its rightmost bit. 7 mod 2. That's, again, odd, so I get a 1. Then I want to shift away that 1 from 7. 7 integer divided by 2 equals 3, right? Get the rightmost bit of 3. 3 mod 2. That's 1 because it's odd. Shift away that 1. 3 integer divided by 2. That's again 1. 1 mod 1. Or 1 mod 2, sorry. 1 mod 2. That is, well, it goes in 0 times with 1 left over. 1 integer divide by 2. That's 0. And then we know we're done. And every time we took a modulus, we got a new digit. Because this is a binary digit, it's a bit. 1, 1, 1, 1. And you read it off backwards. This is the first one. 1, 1, 1, 1. Okay? And so it's 1, 1, 1, 1, base 2, and that is indeed our answer. And you can always check yourself, because you know how to convert from this to decimal again, right? So that is the trick. That's how you can convert to any base. Just replace all this with the base you're converting to. So you can convert a number to base 5 if you wanted to. And I want you to try that now, okay? So convert 117 to base 5, please. Try that, and that will convince you that you understand this algorithm. Okay, so assuming you gave it a good shot, let me do it for you. Remember that base 5 only has the digits 0 to 4 to work with, and that makes sense. That's the only remainders that you're ever going to get when you divide by 5. So let's do it. 117 is what you start with, and then we want the rightmost base 5 digit, so we're going to mod by 5, the base we're converting to. And I have no clue what this is supposed to be, so we can either put it in C++ or I can cheat and I can use Python. So Python also has a modulus, and I don't have to compile Python code. 117 mod 5, that's apparently 2. There's 2 left over. And then 117 integer divide by 5 is something. In the Python language, I have to use 2 slashes. That's 23. Okay. Cool. And so we just shifted away that 2 digit from the base 5 number. Now if I just convert 23 to base 5, we will be done. So 23, let's get the rightmost base 5 digit. And so we can do this one on our heads, right? So 5 goes in 4 times because it makes 20, and then we have 3 left over. Right? And so then we can do 23 integer divide by 5. I think it's going to be the 4, right? 23 integer divide by 5, that's 4. Cool, and then we can do 4 mod 5. Goes in 0 times with 4 left over. 4 integer divide by 5 is 0.8, so it's 0, right? And that's how we know we're done. And we read off the number backwards. So every time we took a modulus, apparently it's 432 in base 5. 117 is 432 in base 5. And we can check that, right? We can check it because we can just convert this right back to decimal. That's 2 times 5 to the 0 plus 3 times 5 to the 1 plus 4 times 5 squared. And I'm pretty sure that's what we wanted, right? That should, you can check it. That's going to be 117 base 10. Okay? So that is the algorithm that I want you to remember to convert any decimal number to whatever base you want. And that with going from any base to decimal, that gives you everything you need, right? You can go one way or the other now. And so that is everything I wanted to talk about there. Let's go back to programming stuff now. So this table, I've taught you some words now, so this should make a lot more sense, okay? Ints, for example, they're made up of 4 bytes, so you need 32 bits, right? Because every byte is made up of 8 bits, so it's a 32-bit number, every integer. And this is how much you can store in a 32-bit number, apparently. There's a special way of encoding negative numbers that I haven't talked about yet, and we'll get to that later in the class. But I think you can imagine this isn't too far off. You can see how the 32 is creeping up a little bit. Chars as well. They take 1 byte, right? You only have 1 byte for a character. You can make 0, 0, 0, 0, 0, 0, 0, 0, all the way to 1, 1, 1, 1, 1, 1, 1, 1. And if you convert this, it's 255, right? So you have the potential of storing 256 different numbers. We just find a way to make some of those negative is all, okay? So that's how we store every integer number. It just looks like this in binary. Doubles and floats, they look a bit different. They're stored in a very special way, but you can imagine there's a lot of precision there because you have 8 bytes of worth of number, right? So you have 64 bits to work with, 64 binary digits to make up your floating point numbers. So they can get huge, and they also have a lot of precision, 16 digits of precision in like the scientific notation version of the number. Okay? So that should make slightly more sense now, and I think your book goes into it even further, but that's as far as I want to go in lecture. Okay? So that is our types, our integer types, our number types in a nutshell. Okay, so back to programming stuff, I want to talk about some new things. The first is constants, okay? You can, I guess this is called like a qualifier. You can qualify any type. You can put const before the name of any type in C++ to make a constant, okay? A constant variable cannot be changed after it's initialized. So for example, I can make const, instead of saying double pi equals 3.14, and then being allowed to change pi later, we can say const double pi, which makes sure that we can never change that variable again, which makes sense for things that should never change, like pi. Yeah. So let's do that. Const.cbp. So const double pi equals 3.14. You can print it out. You can use it just like a normal double. The one thing you can't do is change a constant, okay? So I can't say pi equals, I don't know, 3.0 now. I'm redefining pi to be something easier. This won't even compile, all right? So when you can, and you know you have a variable that doesn't need to change, just say const in front of it, because then the compiler is going to stop you from doing silly things, okay? It'll make sure that you don't give a new value to that constant. That wasn't supposed to change, okay? So that's a constant, not too bad. And now I want to talk about something extra specially important, and those are function calls. I've said this word a whole lot now. We make a main function every time we write our program, but we don't really understand them yet. And so I've had to just let it all be magical for a while, and now I'm ready to teach you what it all means, okay? So let's talk about a function call. All right? Because we've used these before. We've done things like s.at and things like that. That's essentially a function. But this is what it looks like. You have some piece of code that somebody else has written for you. It's called a function. And you want to use that function with some values. Okay, so this is the syntax. You say the name of the function, and you give it some things called arguments. Okay, so here's the idea. A function, it's a piece of code that you can call multiple times, we say. It's like you're yelling to it. Please do this thing for me. A function can take 0 or more things called arguments, and those control the way the function executes. Control the way the function does its thing. Okay, so like there's a square root function, there's a random function in C++, and we'll get to those. Okay, and it's quite nice because we don't want to ourselves always like code up how to find the square root of a number. No, somebody's given that code to us. We can just use it. It's super nice. So that's what a function is. It's just a piece of pre-made code for us. And they usually give back an answer. Sometimes they don't, but usually they do. And whenever you make a function call, the syntax looks like this, and you can just pretend that that function call will be replaced with whatever the answer is that it gives back. So without any further ado, let me show you the random function. That's the easiest one to talk about. So inside of a library that I'll show you in just a second, there is a rand function. It's just like this. It's called rand. And it takes no arguments. You just call it without anything at all. You say rand, open parenthesis, close parenthesis, and what it does is it gives you back a random number. So this whole thing gets replaced with a random number, essentially. And it's whatever it was feeling like at the time, like, I don't know, 1987, something like that. And when you call it again, if you say rand a second time, it'll give you back a different random number, because it's random. Isn't that nice? So that is the simplest possible function. There are others. There's like the pow function in C++. You can say pow of a base to an exponent, like 2, 3. It takes two things, the thing that's at the base and the thing that's at the exponent. So that is going to give you back 2 to the power of 3. So that'll make the 8 for you. Okay. And that is a function call. You just say its name and you give what it's expecting. The power function, it makes sense. It needs two things, right? It needs the thing that you're taking to an exponent, and it needs that exponent too, right? So it takes 2 arguments. But random, it just needs to give you a random number. It doesn't need anything extra. Okay? So that's pow, that's rand. And then there's also square root. Square root looks like this. It's SQRT. And then you can ask for the square root of a number, 2.0, and it'll get replaced with that answer, right? And so if you see out it or something, it'll look like that, and it'll just print that 1.41 whatever. Yeah, that's a function call in a nutshell. That's the syntax, and here are some examples. And now let me show you it in real code. Okay, so yeah, the math functions exist in one of 2 places usually. There's the C standard library, C_stdlib for short, and then the C math library. Okay, and we can look up what is inside of all of these libraries at a very nice website called c++.com. So you can go to this website here and look up stuff, or you can just search Google for C++, the name of the library you're interested in, and it will take you to that website also. So for example, this is the C standard library, and here are all the functions that are defined inside of it. And you can click on any of them and see what they do. Yeah, so that's C standard library. There's also C math. Where's that? Here it is. I'll just keep them both open. And so here's all the functions that exist in the C math library. Super nice things, right? Here's my pow and my square root. So let me show you those things. Let's do, I don't know. Oops. Functions.cpp. So let me at least show you these guys that I've been talking about. So let's include C standard library. This one gives us rand, and let's include C math. That's where square root lives, and that's where pow lives. All right. So if you're interested, you can click on what these are doing. Like, okay, what does square root do? Click it. And then it shows you information about it. It's like, okay, square root takes a double, gives you back a double. That's how you read that. I'll teach you more about that syntax later. And it gives you a nice cute little example of it in use, shows you the output and all that. And then there's plenty of words about it as well. So hopefully you find this website helpful. You're going to live here for most of this class, okay? Very helpful. So yeah, let me call these functions. So cout square root of 2.0. And so this is a call to this function. It's saying, hey, square root, go and do your thing. Give me back an answer. Take the square root of the number 2. Oops. Looks like I forgot to save. There we go. Whee! And so we get the square root. Yay! And you can do pow. Be like pow of 2 to the 3.5 or something. It doesn't really matter. Yay! So it's apparently that's the answer. And then there's rand. Whee! And that gives me back a random number, which is apparently something very large right now. You could get any number, right? So, and there's a lot of ints. So it makes sense to get a big one back. So that's our random number. And yeah, these are 3 function calls. I hope that makes sense. So let me go into more detail. Let's look more at this stuff. I want to talk to you about a few of these, especially round, because that will be used in your next lab. All right, so let's look there. Going to C math, you have sine and cosine, stuff like that. You can say sine of some number, and it's got to be in radians. And here is a nice one, exp. exp. So it takes a double, gives you back a double. This gives you e to the power of that x. All right, so that's the exponential function base e, we say. And so here's a nice example of it. But you just say exp of something, and that something is what you want to take e to. So you can see out exp of 1, for example, and that will give you back e to the power of 1, which is just e. Okay, so that'll work. Dun, dun, dun. There's a trick with randomness, and I'm going to show you it later, so I'm going to comment this out right now. Cout exp of 1.0. And so there's e. It's a nice way to get e. And then we have two words that are useful to know are seal and floor. So this is like a metaphor for a house. This is the floor, and this is the ceiling, right? And so ceiling rounds up a number, and floor always rounds it down. So technically, integer division, you can think of it as normal division with a floor baked in. All right, so here's what those 2 functions would do, 2.15. If I take the ceiling of 2.15, CEIL, and I call it like that on 2.15, it'll give me back 3. If I call floor, ceiling always rounds up. Floor always rounds down. That'll give me the 2. Okay, so those are 2 useful words that you'll hear about later if you take another math class, maybe. And then you have normal rounding, which I'd like to show you too. All right, there is a round function in CMath right here, and that rounds to the nearest number, which is the rounding that we know and love from math, right? So if I were to say round of that 2.15, that would give me back the normal 2. And then if I were to round a number with 0.5 or above, right, 2.5, that would round it to 3 because that's closer now. Okay, that is our normal rounding. So let me show you that. Just call the round function on your number. Not a big deal. And then 2.5. So I got my 2 and I got my 3. Okay, that's rounding. That's useful to have. Yeah, so that's a lot of C math. There's also C standard library, which is more than just math stuff. You got your randomness, which I'll show you more about on the next slide. You can get the absolute value of a number here. That's what abs is doing. There's a lot of cool stuff baked in that I encourage you to look at. Just click on these. They all have examples. They're super nice. Exit is also nice. The exit function stops the program immediately wherever you are. That'll be useful later. Yeah, anything else? No, I think that's all I wanted to talk about here. Let's go on to random numbers. Okay, so yeah, rand, like I showed you, it gives back a random number between 0 actually and a special constant called rand max, which is a very large number. Okay, so I click on rand, it's going to tell me all that stuff between 0 and rand max. I can click on rand max, and it's apparently at least this, but it's usually huge. Okay, at least for later versions of the C++ language. So it's just a random number between 0 and some giant number. That's what random the rand function gives you. And there is a problem with it. So let me show you that problem. I'll make a new file called just rand.cpp. So if I want rand, I got to use cstd.lib. And watch this. Cout rand. So I'm going to write this is a program that just computes a random number and shows me that random number. There it is. This was the random number that it came up with. And so if I rerun the program, surely I'd get another random number. Oh, well, I guess that's possible with randomness. That's totally a possibility. Oh, it's still that number. So surely something is wrong. Every time you compile this, it's not going to change the first random number that it comes up with. The next one is going to be a different one, of course, but it's always going to be the same different one, right? These are two random numbers that never change. That is unfortunate. And this is because of the way the random function works. It's not truly random. It's doing some fancy math that makes it look random. So the rand function is really secretly calculating a random sequence of numbers. So like you call it once, it gives you back 1. You call it again, it gives you back 42 based on that 1. You call it again, it gives you back like 85 based on that 42. And it's just a sequence. That looks random for all intents and purposes. But the issue is, random doesn't know to try a new starting value for that sequence that generates its randomness unless you tell it to. So there's a second function called srand that we say seeds the random number generator so that it gives us a different sequence of random numbers each time we run the program. Okay? So we need to seed the random number generator, we say, with some number that changes each time we run the program. A nice number that changes every time we run the program is the current time. There's a way of converting the time to just a number. It happens to be the number of seconds since January 1st, 1970. That's how time is stored inside of computers. That's a long story. But if we just use that, give that number to srand, that's part of the ctime library that gives us this, that will allow us to have a different number each time. Okay? So that will be nice. Let me show you that. Ctime. So this one is for rand, and this one is for time. Okay? So the first thing I need to do when I'm going to use randomness in my program is I need to seed the random number generator with the current time. That way, every time we call rand, when we run the program again, it'll be a different number because we're starting it in a different place. It's a little generation process. So you say srand, and then you give it the current time. And the current time is got by using the time function with 0 as its argument. Okay? So that's just a line you got to memorize. I can explain it more in office hours if you'd like, but that's as much as I want you to know here. And now when I call rand, it'll be different each time. Whee! So I get these big numbers. And then I get these big numbers. And one's not so big. And so now it's different every time. It's really random for our purposes. Okay? So that's super nice. Now, let me check time. You might be wondering, well, sure, I have some nice big random numbers, but I don't really usually want big random numbers. I would like maybe in my program, maybe I'll make like a guess the number game. I want to make like a random number between 1 and 100 or something. Why can I just do that? And the answer is yes. Let me show you how. So the trick is, let's try and get a random number between 1 and the user's choice. Let me show you how to do that. Okay, so let us ask the user for the upper bound, up to or something, I don't know. Cout, enter a number, and we'll store it in up to. And our job now is to output a random number. between 1 and that number that we're going up to, which I have called up to. Okay? So if the user types 10, we want a random number between 1 and 10. If the user types 100, we want a random number between 1 and 100. Let me show you the trick. Dun, dun, dun. Let me show you how to get a random number between 0 and some other number. Okay? Watch this. The trick is modulus. You remember that? What does modulus do? It gives you back an answer between 0 and this number minus 1, because that's the remainder, right? That is the trick. That's how we're going to shrink our numbers down. So if I say rand, and I say mod something, mod some number, the answers that I will get back, because rand is some number, could be anything, the possible answers that I will get back are 0, if it, like, there was no remainder, 1, all the way to num minus 1, right? Because if you're trying to do remainder dividing by 5, you can only have remainders between 0 and 4, right? Because if you had remainder 5, you could just add a new 5. It could go in one more time, right? So it's up to num minus 1. And this is how we're going to make it work. Because this gives us a random number between 0 and num minus 1. If I want a random number between 1 and num, then I can just add 1 to whatever number I get back here. You see that? I want it to go from 1 to num instead of 0 to num minus 1. So I just take whatever number I get back and add 1. Plus 1. And that gives me 1 to num. Does that make sense? That's the trick. Let me draw that cleaner. Num. So modulus saves the day here. That'll give you a number between 0 and that number minus 1. And then if you add 1 to it, that'll make sure that that number is between 1 and num itself. All right. So that's the trick. Let's perform the trick. So rand mod up to, take that result, add 1. See that? That's useful. We enter a number 5. I get my 5. 5. I get another 5. 5. 4. Yay. 5. I guess it's really 5 happy today, but I promise it gives you every possible number. Okay, I get my 4 again. 2 this time, yay. Let's do 2. So it'll give me a number between 1 and 2 every time. 2, 1, 1, 1. It's only got 2 options, right? There's the 2. So that's really working. It's going to be a random number between 1 and up to. If we do it for 100, 1,000, super useful. Okay? You can make a random number generator and like a guess the number game or something in code. We'll do that later in this class, actually. So that's random numbers. Then I want to teach you about some more stuff you can do to strings, because they're technically function calls. I showed you like the .at on strings. It looks a bit different though, because there's a dot involved. It's like you're acting on S itself. So it's like a function, but there's extra stuff going on. So this is called a method call, if you care. We'll talk about the real difference later, but it's really just a function on strings. You just got to remember the name of the string and then a dot for now. But all this stuff that you can do to a string exists in the string library. So that's in other here. You can go to string. Here's all the stuff you can do to a string if you click string, the type. So here's all the stuff you can do to a string. You can ask for its size. You can say string s.size, for example. Whee. So here's an example of it being used. So it takes no arguments, and it gives you back the size of that string. So let's pretend I have a string that says hello or something. So string s equals hello. For example, that would look like this in memory, right? It would have those characters H, E, L, L, and O, and those would exist at indices 0, 1, 2, 3, and 4. So some nice things that you can do to strings are ask for the size of that string, and that tells you how many characters are in it. So I'll show you that. So some more string stuff, strings.cpp. So I need the string library. So I'll make a new string called s, and I can do s.size. That gives me the size of the string. compile and run. I get my 5 because it's got 5 characters in it. Makes sense. You can also add strings. So the plus operator is overloaded for strings. So if I have another string, I can add them together. So if I had S1, that was like hi and a space, and then S2 was mom, then if I add them together, it would make hi mom. Okay? S1 plus S2 gives me back a new string that is hi space mom. Okay? That's useful. There. So, I'll show you that. So, string S3 equals S1 plus S2. And then I can see out S3. And it's just going to put these strings right next to each other. Add the characters one after another. So I get my hi mom. Cool. All right, some fancier ones. You have find, replace, and substir. So let me show you those. Find is quite useful. Find gives you the first occurrence of, you can either give as an argument a string or a single character, doesn't matter. You find the first occurrence of that character slash string inside of the original string, S. So this is asking, hey, S, look for the character H inside of yourself and tell me the index where that H occurs first. Okay? That's the idea. So that's the index of something. So for example, let's work with S again. So I can output S, or int position, let's say, equals s.find. Where is the E character in S? Please tell me. And of course, it exists at index 1 in the string S. Do you see that? So it's going to output 1, if it's there. If it's not there, it makes it -1. It gives back -1 because that's an invalid index always, right? Let's look for the character, I don't know, L in the string S, which doesn't exist. Oh, sorry. Of course it does. How about P? P does not exist in the string S. Okay, so it's not there. It can't find it anywhere. And so it's going to be -1. Whee. And that's how you know it's not there. Okay, so that's find. Replace is another good one. Replace takes 3 arguments. You have a string, an original string, and what it does is it takes a starting index, it takes a length, and then a new string to replace. So there's a lot going on there. Let me show you first the library information page. There's replace. Boop, boop, boop. And so what it does is it's going to overwrite the string itself, actually. So it's going to mess with it. So here's the idea. It's going to takes another string, takes a position, takes a length. What do they mean? I think the best example would be for me to show you in code. Let's see. I think I had a good example, so let me quickly look up what my example was from before that I wanted to use. Yeah, so let's turn hello into hola. That was my fun example. Cool. So here's how you do that. You would say s.replace, and here are the fancy numbers. It's going to be 1, 4, and the string OLA. And here's why. Changes S from hello to hola. And so the first index is your starting index from where you want to change the string. You're trying to replace pieces of it, right? So from index 1, please erase 4 characters. That's what the second thing means. That's the length that you want to change, the length of this substring, we say, that we want to change from the inside of the string S. So starting at index 1, go 4 characters and change those 4 characters instead of what they were to OLA. So delete them and replace it with this. Okay? So what it's going to do is it's going to start here, index 1 of string s, delete 4 characters, 1, 2, 3, 4, and please add instead OLA. See how it's going to change it now? That is the trick. That's what it's doing, and this edits the string in place. Okay, so if I output s again, it is now going to say the new thing. All right? So that's the trick for replace. It's always starting index, the amount of characters that you want to replace starting at that index, and then what you would like to replace those characters with. It doesn't have to be exactly 4 characters. You can replace it with something smaller or something larger. No big deal. So that's replace, probably the most fancy. And then subster also is a good one to know. So subster is going to take a few characters. It's going to take len characters, so the number goes in the second spot, from s, starting at index start. Okay? So let me show you that. So if I wanted, I don't know, now s is equal to ola, right? Let me, I don't know, let's output LA. Let's make that string. Let's get out the inner substring, we say, la inside of ola. All right, so it exists at, where does la start? It starts at index 0, 1, 2 of the string s. And how many characters long is la, the la that I want? It's 1, 2. Okay? So I want to start at index 2, take 2 characters. That's how you use substring. And sorry, it's subster, excuse me. Stands for substring. So the first one is your starting index, just like for replace. And then you give how many characters you want to get out, you want to extract. An inner, smaller string, a substring from s. Okay? So this will give me the la. That is the la right there. So starting at index 2 of the string, so 0, 1, 2, starting at the L, take 2 characters, please. So take the L and the next thing, the A, and give me back that string. So that is subster, and that is the idea there. So that's taking len characters from s starting at index start. So those are a few cool string operations. I encourage you to look at the rest of this library page. Plenty of other cool things that you can do to strings. Okay. Yeah, I think the last thing that I want to do is ask you a question. This is not in person, so don't worry about going to the class website and writing in the Google Doc. You can if you want to, but I would like you to think about what the difference between 1, 2, 3 and 1, 2, 3 in quotes is when you see it in C++. So pause the video, think of all the differences between those 2 pieces of C++ syntax, and tell me what you're thinking. All right? Either telepathically or come to office hours and we can talk about it. All right. So what is the difference between 1, 2, 3 and 1, 2, 3 in quotes? Because there is a huge difference, right? 1, 2, 3 is a number. Precisely, it's an int. And you can only do number stuff to it, right? You can do the plus, the minus, star, divide, mod, do pow. You can call pow of this with another thing. You can call square root of that number. It's a number. You can do number stuff, right? That is quite different from 1, 2, 3 in quotes. That is a string. It's a bunch of characters, right? And you can only do string stuff with strings, right? There is no minus on strings, but there is a plus. It just does something completely different, right? It adds characters instead of numbers. You can get the size of a string. You can pick out inner bits of that string, a substring. That's all you get to do. There's a huge difference between the two, right? And you have to be very careful about which ones you're putting in certain variables. Like you can only put numbers inside of ints, right? It's got to be the 1, 2, 3. It can't be the quotes 1, 2, 3. That wouldn't even compile, right? And so think about, like, even the representation is different. Like this is a number, it's 32 bits long, because that's what an int is. But if we had the string s equals 1, 2, 3, it's 3 characters long. The character 1, the character 2, the character 3. No concept of numbering going on here, right? This isn't like the hundreds place or anything. It's just the 0th index of the string. Okay? Hopefully you see the main differences here, and that's just something to remember. Okay? You can only do, like, the type determines what you can do to a thing. Okay? And that's a very important concept in C++. And so that's why I'm hitting it hard here. But that brings us to the end of these slides. We did it. So you are now experts in variables, assignments, math, and strings. Oh my. So that's all I wanted to talk about today. I will see you in your lab video now, because I'm going to introduce your next one to you. It's going to be lab 1. All right? So I'll see you there.